I now often have the birthday celebration Taiwan because the very less people know this. But I don't know. Professor Barroso, the mechanical engineering, he told this news to everybody here in Realtek. So yeah, I'm so happy. Yeah, thank you for the greeting. Yeah, not only good wishes for your study. Okay. And sorry, no cake issues. Anyway, yeah, if you have any problem about this course or in the future you want to study in Taiwan, yeah, highly welcome. You can ask me anytime. Yeah, and also we can I have two students here. Charlie, and James. Try to communicate with them. Give the message. Yeah, keep contact. If any problem, contact me or fine, contact Charlie or James, fine. Both of them, they will stay here until the middle of November. So you can not the time to contact with them. If you have any problem, you can go to the national office, contact them, Charlie or James. Okay. So any questions you would like to provide you? Yeah. You want to know more about Taiwan? Taiwan right now is very good. Master. And we'll start the stipend and the scholarship for your application. So highly welcome you to contact us. I think it's also one purpose why I'm here. Not only deliver a course here. The course is very briefly, very easy. But I think the important thing is that you know us, know the Taiwanese people, and also know Taiwan. Yeah. So we can cooperate together now. We can cooperate together. Even co-work together. Okay, continue to talk about this issue. Try to finish the problem about the thermal buckle. So once again, I emphasize here polymer. Polymer, because the thermal expansion coefficient is 1 order. You know, when we turn 1 order of magnitude, it means 10 times. 1 order is 10 times. 10 times, right? 10 times larger. 1 order of magnitude larger than the metal or silicon. So the working temperature is 1 order of magnitude smaller than metal and silicon. So it's good for us to provide you a low temperature process. And Parylene here is one kind of polymer we can use. It's a deformable membrane and a pumping piston application here. And the photoresist is assigned as a sacrificial layer, not sacrificial layer. Pertinent or gold heating element, heating electrode embedded inside the Parylene membrane. So finally, we integrate Parylene, photoresist, and the metal with the valve. So finally, we have the micro pump. Pumping the fluid into chamber or channel. So the process we have mentioned that before, and it's the final device we have. The silicon. Finally, the cupping this chip from the silicon wafer. We do the dicing soul cupping, so you can see very beautiful shape of the chips at the head. We also doing the finite element simulation. Finite element simulation about the temperature field. Also the thermal buckle max deformation. Thermal buckle deformation. So AXIS is a very popular finite element method in calculation the result some mechanics field. The Parylene membrane heat up only to 40 degrees. Only to 40 degrees. And show that the simulated maximum diffraction is about 2.8 micron. So it's very obvious, very obvious. So this problem is the multi-physics problem. We have thermal, temperature field. We have stress, deformation field, right? Heated and deform, heated and deform. So in the multi-physics coupled together, temperature field and the force field contact coupled together. And for the displacement measurement, simulation is easier. You use computer to compute to know the displacement. But what is the real displacement after fabrication and the testing? It's a question. Because right now the device is very small. The total size only 300 meters in diameter. 300 micrometer. 3 times our hairs diameter. It's very small. So it's very hard to justify, to measure the temperature coefficient like this. Our temperature field is very big area measurement. But right now our touch is very small, only 0.3 millimeter. Very small. You even take the point though temperature is hot. Not to say about the distribution. Right? So maybe we can only detect 1 point of temperature to denote the overall temperature behavior. So actually it's not easy for us to do the temperature measurement in that small scale. So how about IR? Even for displacement, laser beam size is comparable or even smaller than our membrane. Another one is how about the temperature field? We use the infrared, right? Infrared image. Infrared imager try to help us to realize the temperature distribution. But unfortunately, you see, the wavelength, so IR is 8 to 15 micron. Very big, very big. So in other words, maybe we cannot obtain. If 1 pixel, you mean the 1 pixel of the temperature field is 8 to 15. In other words, maybe it's very hard. 1 spot of the measurement maybe at this size. So if the overall membrane maybe only allow you to have the 8 point or 9 point measurement. Very, very inaccurate. Not accurate at any point. So even for IR detect, very hard, very difficult, very difficult. So the best way in the future is we directly integrate our temperature sensor inside our actuator. So right now, comes up with the idea. Right now, we are not realized, but should be realized in the future is, okay, you have an actuator. Actuator is hard to make, hard to work, but also hard to verify its performance. Very hard to verify its performance because we have no available measurement instrument and detect small size behavior. So in the future, we need to integrate micro sensor inside. We have mentioned RDD, right? RDD, right? So there you go. Last week we have mentioned RDD. RDD maybe need to implement in our system. You should use the micro temperature sensor to detect the behavior of the micro pump in the integration manner. Or you should integrate micro temperature sensor or even the micro displacement sensor in the micro actuator so as to output the actuation situation. So you mean that now this course is sensor and actuator. In the past, we separate two interesting. We tell you what is the sensor, right? And we tell you what is the actuator. But finally, if you want to let your system very powerful, you should implement the sensor and the actuator on your device at the same time. At the same time. Okay. So it's not easy to do that. It's not easy to do that. But if you can make it, your system will be very powerful. Will be very powerful. Okay, regarding the displacement measurement, this is a bulky way. Bulky way means that we use a big machine to measure your small chips. So not accurate, not great. Now the laser beam maybe has a similar size to our device. So when you measure the data, they tell us the maximum vertical displacement is about 350 nanometers, is about 0.35 micron, much larger than our maximum point, about 3.8 micron, predicted by numerical method. Very far away. So we just guess maybe we underestimate. We underestimate the measurement. This estimate may be underestimate because it uses the optical method. Optical it's the optical interference method. So not so accurate. So maybe hugely underestimate our performance. So we have a video. We have a video about this. Maybe we talk about this measurement. Okay, then you have the idea. This is a pump. It seems not vibrating, but if you look detail about that, you can see some vibration about the electrode. You can see some vibration of the electrode. And there's a particle here. You can see it vibrate. Vibrate. So it means that we have the pumping the membrane and try to push the particle, push you forward. That's over here. That's over here. The displacement here is very apparent, and then gradually not so apparent because right now the channel bigger, wider and wider. So the flow speed getting less. So this is our electrode. We apply voltage here and try to make the thermal buckling deformation. Thermal buckling deformation. So we have mentioned that frequency response. What is frequency response? It means that we can change the frequency of our driving voltage. Our driving voltage is the AC. We're driving. You know, our driving is not the DC driving. Our driving is you can use the sine wave, or a triangle wave, or square wave. It's the AC wave to do the driving. It means that sometimes positive, sometimes negative. Sometimes have the you can define your duty cycle about your AC and trying to identify from the slow vibration frequency to the higher vibration frequency, and to measure the displacement by the previous bucky machine now. And you can see the Parylene is much softer than silicon, very soft to be vibrating. So it's a low frequency. Still keep a total frequency about 500 meters, 500 hertz. It means that in 500 hertz, about here. Hertz is about here. Have the 3 dB, minus 3 dB. It means that the strength or the displacement only 1/2 of your maximum displacement. But at least you can understand even for several functions, the hertz AC driving is still feasible in our micropump. So the frequency behavior is not very bad. It's still acceptable. Where the resonance is the frequency response. And how about the image? How about the IR detection? We also use another puppy, thermo cam, with a thermo IR camera, very big, but the pixel size is not good enough due to the cost of the machine is not very high. So the pixel size only approximately 1 meter. 1 meter is larger than our diameter, 300 micron. So we strongly underestimate the temperature. So the temperature measured is not so high as 2.8 degrees. No, it's not 40 degrees, but only about from 24 ambient temperature to about 31 degrees C. Only several degrees C high. But we underestimate. This part is our heating part device, very small. So underestimating the maximum temperature in this measurement is fully underestimated. It should be as high as about 60 degrees. About 60 degrees, 60. But due to the underestimate, we take the average of the bigger coolant press, cold press. So the final average value only 30, 31. Very far away, lower than our expected value. So it's IR detection. So finally, we get a conclusion. The conclusion is the best way for us to make an actuator is try to integrate microsensor together. You design the actuator is fine, but you should design the sensor assigned to do the measurement, to calibrate the performance of actuator at the same time. It's the best way for us. So sensor and actuator cannot exactly separate. You should try to combine together to make your system wonderful. Okay, so I complete the part about thermal actuator. The next topic is electrostatic actuator. I hope I can finish this part. Electrostatic actuator is also very good for our microstructure, micro actuator. We're going to talk about electrostatic force is a kind of surface force. Surface force is very compared to gravitation, body force, small scale. So it's good for our actuator. So one example famous is Texas Instrument DRP, digital light process for our projector. So in the DRP, there is a DMD, digital mirror display. Mediums the digital mirror plate, mirror operate individually. So medium, you can see mediums the micro mirror and the complete image manipulator. And the ear of the mirror array must be 100% perfect. So how do we do it? Drive the voltage, electrode pull-in happen, diffracting the light beam, and finally modulating whole image. I think the most important concept here, what to talk about is electrostatic pull-in. Electrostatic pull-in. What is it? Pull-in is the phenomena So it's unstable behavior of our electrostatic actuator. For the previous case about the thermal actuator, we know if we want to make our actuator permissive and function well, we need to decide their stability, make the system unstable. Make the system unstable. Unstable means the output is very big. So you can have the large actuation force outside. Because right now we only want to make only single one. Single one, you must make it very unstable. We don't care about it will be fail or not. It will be fail or not is not your concern. Your concern is that you need to make it behave very big output. So similar in the electrostatic force. Here is the capacitor. This capacitor has a separation T0. It's the initial gap for this capacitor. And then we have the structure stiffness K value, very similar to the spring constant of a Hooke's law. It means that we can let the capacitor to change the gap. Very similar to our capacitive sensor we talked about yesterday. So the total capacitance is like this manner. Everybody knows that. So we calculate the electrostatic force. We calculate the energy, force, and so we have finally have the two kinds of force. One is electrostatic force. One is spring force. The structure. Our structure will pull down by the electric field, but our structure has the repulsive. It means that we want to back to our original state. Right? It's something that spring. We have the deformation. We want to restore to its original shape. With the spring force, back force. Two forces try to pull to each other, try to compete. They try to compete. So we plot these two kinds of force in this figure. Vertical axis is the force. Horizontal axis is our gap. It's the gap of this capacitor. So this capacitor, we can change. Okay, so the straight line is spring force, is our structure. Our structure means that we have a cantilever beam, right? It's our capacitor electrode. It will bend in, maybe it will pull down. So we have diffraction. So your D will change. And then it obeys the Hooke's law, so it's a straight line. This is spring force, a straight line. And another one about the electrostatic force is what? Is inversely proportional to D. It's nonlinear. I don't care about nonlinear. Nonlinear is like this. Okay, we have curve. The curve is our electrostatic force behaving. So right now we have two kinds of curves. One is line, one is curve. We try to do the discussion, want to discuss what the interaction of these two cases. So how about the interaction between the spring force and the electrostatic force? Three possibilities. First one, okay, let's fix the spring force at first. This line, if we let this line fix, right? just across the original point 0. So this straight line is fixed. We change the voltage of our electrostatic force. So this F static will go up or go down. Because you can see the voltage, right? You can change. We change, then the position of the electrostatic curve will change place. So you have three possibilities. One, you intersect with this line. We have the 2-point intersection, right? You have 2-point intersection in the first case. Number 2 is only 1 point. Only 1 point. Tangential to the curve. Only 1 point. One solution. The number 3 is no solution. No contact, right? It means if your voltage is too high, your curve is here. Nothing to do with the straight line here. No intersection. So 3 cases, right? What about the first case? For the first case, 2 intersection. 2 intersection means what? Only one of them is realistic. Another one is not realistic. So only one is realistic. So what is the realistic? Actually, the point here is realistic. Very close to the minus d0. It means the only small deviation from our original d0. So this point is visible. This point is visible. It's a true solution. It's a true solution. In the first case. In the first case. And in this case, our capacitor plate only has small deformation and stuck up there. Force equivalent. Force equivalent. Spring force and the electrostatic force equal to each other. So only small deformation happen. So nothing very. It means that no strong, no apparent deformation can be observed. Another case is no solution, right? What is the no solution? No solution, a little bit hard to image, right? It's a little bit hard to think about. And what is the no solution? Huh? So, okay, we cannot image what is it. Let's think about this second case. 1 point. What is the 1 point? 1 point. 1 point means, right now the deformation is not very small. A little bit bigger, right? From this value to this value, bigger, not bigger. Only 1 point. Only 1 point. So at this point, it's very critical, right? Only one solution, and it exists, right? No. Other case 2, only one is true, another is not true. For this point, it should be true, but very critical. It means that in this point, it means that it still has an equilibrium, right? Equal. It's two kinds of force equal. But if you increase the voltage a little bit, if you increase the voltage a little bit, the deformation a little bit higher, what situation happens? The curve will leave the straight line, right? Will leave the straight line and no more intersection. No more intersection means the electrostatic force always larger than the spring force. Attraction force always larger than the spring force. So what happens? The deformation will be continued. Understand? Your attraction force is larger than your drag. So what happens? Keep tracking. So what is the destiny? What's the fate of this electron? contact. Understand? Keep deformation until contact. Fully attracted. Start off there. We call it the what? So we call it the pull in. You mean that for this the full line, right? Before this full line we have force balance. But after this full line, everybody come to my side. With a pull in. It's a matter of unstable phenomenon. Unstable. Unstable phenomenon. So understand? So it's a matter of unstable. Unstable. So unstable is very important to our micro-actuator method. If you think back to our thermal actuator, what type we're talking about? Buckle, right? Buckle means the structural collapse, but not really collapse. Function very well. Okay, right now in electrostatic, we also have the unstable. It means that we pull a little bit and then beyond that limit, wow, unstable, large deformation and collapse. You know, thinking I collapse means I fail with this device, but not fail. Not fail. It denotes a very large deformation. I like this. I like the large deformation. If no large deformation, how can you push others? Right? How do you actuate others? So understand, for microstructure, small deformation is your destiny, but we try to amplify it, try to make it unstable. Make it unstable. So it is another thinking way. It's not another thinking way. And this result is also very interesting. This derivation are very difficult, not difficult, complicated. If you have the file, I give the file to several people. You can. We only noted this result. This result is what is the critical displacement. This point. What is this point? This point is from 0 to 1. In only 1/3 goes to 0. If you have the displacement, for example, originally I have the 3 micron gap. If I induce 1 micron gap, I no more use any kind of extra moment. You will keep attracting. So you only push 1/3 the original displacement and enough. So it's a very easier way for you to understand it. 1/3 is the 1/3 of displacement. And it's a voltage they apply. So this kind of phenomena are used in our DLP. Using the DLP function. DLP function. Even for the DLP function, there is a mirror. You are tilting. Actually, they use the electrostatic force to attract. So beyond some angle, it will automatically collapse.